All right, so for this problem, we have two similar sort of setups of things falling, and we're going to solve them in relatively similar ways. Because as we'll see, the first one in part A we could do with Newton's laws, accelerations, multiple free body diagrams, and all that, but it would be really time consuming, and energy is going to be a lot simpler. But from parts B, C, D, and then E, we really can't do it with an F equals ma sense because there's too much changing. We have to really talk about it in terms of energies to get a good answer. So for part A, we have two blocks that are attached with a massless string, and they're on one of them's on a frictionless table. So if we do this with F equals ma, we need to do two free body diagrams. It's kind of a pain. With energies, it's actually quite simple. We start off with the statement that our change in energy is going to be 0. And it's 0 because we're going to make our system both blocks and the Earth. So that means the gravity is an internal force. There's no friction for thermal energy. There's nothing else in the problem that exerts a force on it. So our energy is conserved. And so now before, both the blocks are at rest, and later they've moved a bit, and so they have a speed, and one of the blocks is descended. So our initial kinetic energy is going to be entirely in potential energy. And our future, later energy is going to be in kinetic to start, or partially kinetic, and then less potential. So, to start, we're going to say that the hanging block is, well, actually, I'll draw it rather than try to describe it. So we have two blocks like so, and a tabletop, a pulley, and the other block, right? So we're going to say that right here, actually, yeah, so let's do it a little bit more easily. We're going to say that right here is y equals 0. We know that this top block, even though it's a certain height above where we start, height's not changing, so we don't really care about the top block's potential energy. At some time later, right, this block will have moved, and this block will have moved, and this distance is d. So we can call this y equals negative d to describe the potential energy. And so initially, we start off with 0 energy, because where we defined our 0 of potential. So it's 0 kinetic plus 0 potential. And later on, we have 1/2, I'm going to just put this in quotes for now, m v squared plus m, actually, I'll do that in quotes, another quotes, m, because we're going to clean that up in a second, g negative d, because it's gone down a height d. So now I have to look at these masses a little bit more closely, like these parts. So the kinetic energy mass is both blocks, because both blocks are moving. So that's just capital M, because m over 2 plus m over 2. But the potential energy is only based on that block. That's the only one that's descending. Right? So this is then the way to write that. So we can solve. We cancel the m's. We cancel the 2's. We get v squared is g times d, or v is the square root of gd. And that's part A, sort of the simple setup. For part B, now instead of two point masses, we have a rope that's to the same total mass of the system, but now the mass is sort of evenly distributed out throughout the whole thing. And so we have this picture of our rope hanging over the edge, right, a distance y, and we want to know the gravitational force. And so all we care about is the force on the hanging part, because that's the part that's going to make it accelerate down. The gravitational force that acts on all this doesn't really do anything, just balanced by the normal force. So this, if we know how much mass is there, then we know the force, right? It's that mass times g. And so to do this, we have to think about what this means for a uniform rope of total mass and total length. If half the rope was hanging, then we'd have half the mass, right? So we're going to just find a density as a mass per length, and then the total amount of mass we have here is the density times the length that's hanging, right? That makes the units work out. And we can rewrite that as my over L. So the idea, right, if I kind of circle this bit, is y over L, sort of the fraction of the mass you have is the same as the fraction of the sort of volume of the rope you have. So then the force of gravity is m hanging times g, which is myg over L. Right? All right, so that's part B. Part C, for the work done by gravity, right? If we want to calculate that, your first instinct might be to do force of gravity times the distance d that it travels. Actually, right, which would be like y in this case. But you can't do that because this is not constant. So instead of calculating the work as a force times a total distance, we have to break up that distance into tiny little chunks and then add up the amount of work that's done for each of those tiny little chunks, assuming that the force is constant during those tiny little chunks. And that's the integral concept. So this is fg of y dy, right? The tiny little chunk dy. And we add them all up. And we just found that that force, so we can plug it in, mg over L y dy. And this is a pretty simple integral. Mg and L are all constant, and then the integral of y dy is 1/2 y squared. So we have mg over L y squared over 2. And so that's then the work, right? mg y squared over 2L. That's the work done by gravity as the rope falls, basically. Okay? All right. So next, if we've been careful through parts B and C, part D is fairly straightforward. All we're going to do is we're going to use the work-energy theorem. If our system is the rope, the energy of the rope changes because of external forces, in this case, gravity. So W equals delta E. And in this case, since we talked about gravity as an external force, the change in our energy is only a change in kinetic energy. We've already talked about what happens with gravity by calculating the work done by gravity. So mg y squared over 2L equals 1/2 m v y, I'll just call it v squared. And so we want an expression for v as a function of y, so we can just rearrange and solve. We cancel the m and the 2. So v squared is g y squared over L, or v is the square root of g y squared over L, right? The key is to recognize that gravity is not an internal force. We don't have gravitational potential energy here. It does work instead. We could solve the problem with gravitational potential energy, but then we would have to kind of waste the work that we did in parts B and C. So it's easier to do it in this problem this way. But you can do it with gravitational potential energy if you're careful. Okay, so now part E. We allow our first system from part A and then the second system from parts B, C, and D to fall the distance L. And we want to know the relative speeds. So for the rope, this is V when y equals L. So we can plug that in as a square root of g L squared over L is g square root of GL, right? Because one of those L's cancels. For the blocks, right, we have to go back a couple slides, right? We have this. So if it falls a distance d, we know its speed. So v is the square root of g times how far it falls, L. And so all we have to do is compare those two numbers. And it turns out they're exactly the same. And so our answer should be that the speeds are equal, and then the justification is this math right here. So the problem is tricky, but it's much easier with energy and work than it is with forces and kinematics ever could have been.